Assalamualaikum. So we are going to be continuing solving problems from chapter number 6, and today is lecture number 27 if I'm not mistaken, and we are going to be taking some problems to be solved in chapter 6 and chapter 7 together today, because there are lots of common things that we need to solve together in this regards. So we are going to start now with 6.12. So looking at 6.12, okay, so this is 6.12. So what do we have? We have a transfer function which looks like 5 over 10s plus 1 into 4s plus 1 into s plus 1 to 0.2s plus 1. Okay, so that is the question. And what is required? Find an approximate transfer function of second order plus time delay. So it wants us to find a second order plus time delay that's described this process. Great. So to find out, you remember that we said that for a transfer function, like we can use the Taylor series and the Skogestad method, right? So let's do both methods. Why not? So I'm going to use the Skogestad method. I'm going to use the Taylor series method. So for the Skogestad method, what you're going to do, you're going to keep the first two. You're going to keep the biggest transfer, the biggest tau that is the most dominant here. And as you said, because for a second order, you're not going to touch this. Okay, you're going to keep it, and you're going to start doing all your solution with the rest. So my second order will be some value here that I'm going to find, which is tau s plus 1. Okay, and I'm going to find the k, which is in this case k is equal to k skog, and I'm going to find the theta, right? So I need to find k, theta, and k. So for Skogestad method, if you remember that we said that k skog is equal to k, which is 5. Tau skog is equal to tau largest plus half of next largest, and in this case my largest I'm going to start here and my next largest is here, because I'm talking about the second order plus that time, right? I'm not going to touch this. So I'm going to have my answer going to be like 4 plus 1 over 2, so that will be 4.5, and my theta skog is going to be half of next largest of the tau plus the remaining taus, okay, plus the remaining taus plus theta if I have theta time delay. So what I have here, so I have 1 over 2, so this is half of next largest, 1 over 2 plus 0.2, and that's all what I have. So 1 over 2 plus 0.2, so that will be 0.7, and that's all. So I have my system, which is G skog. G skog is equal to 5 e to the power minus 0.7s over 10s plus 1 multiplied by the tau that I have found, which is 4.5s plus 1. Great. So that was using Skogestad method. What about Taylor series? Taylor series is just like a piece of cake and is simple to do. So what I'm going to do, I'm going to do it directly here. So this is 5 over, I'm going to keep the second order 2 of the terms down here, and I'm going to take the smallest two which are not dominant far away from the imaginary axis to take them as a time delay. So this will be like e to the power minus s and e to the power minus 2s, and in this case our answer will be e to the power minus 1.2s divided by 10s plus 1 into 4s plus 1. And by the way, if you do a plot for both of them, you're going to find that both of them are accurate. So that was the 6.12 for the approximation methods. Okay, great. Now that we have done a lot here, I think so now it's a good opportunity to go to solve the problems that we have at chapter 7. Okay, and to do this, if you excuse me in a moment. So here I'm at chapter number 7. So I have I'm going to start with a problem of 7.1. So let's start 7.1. So what do you have in 7.1? Okay, 7.1 says An operator introduces a step change of the flow rate Qi to a particular process at 3:05 a.m. So he changes Qi from 500 to 540 gallons per minute. So let me write this because I don't want to forget. So I have my Qi is from 500 to 540 to 540 gallons per minute. Okay, so this is per minute. Okay, so this is equal to like 540 minus 500. So this is my step change, which is equal to 40. So if I want to know that in the S domain, so this is 40 over S. That was a quick, I don't know what is required for the problem, I just did it. And that happened at 3:05 a.m. The first change of the process temperature initially at 120 degrees Fahrenheit. Okay, so when you change the flow rate, the temperature changed. So the temperature change was 120 degrees Fahrenheit, comes at 309. Okay, that means from 305. Hold up, but yeah. So what happened? An operator introduced a step change in at 305, but the change happened what at 309. And now that is very clear that I'm having a time delay. That is very clear that I'm having a time delay, which is 309 minus 305, which is equal to 4 minutes. Okay, I think this was clear, right? We did a change at 305, but the change first appeared at 309. And a change from 120, the response is quite rapid, slowing down gradually until it appears to reach a steady state value of 124.7. So it's changed from 120 to 124.7, okay? So the change of the output was 124.7 minus 120, and that is equal to 4.7 degrees centigrade, okay? Well, there's something that I need to mention here. It says rapidly, and I'm not sure that the response, is the response looking something that is like that, or the response is looking at something that is like that. We don't know. Actually, we don't know, okay? Because what? Because we are not sure. We have the initial point and we have the final point, right? So we have the initial point and we have the final point, but we don't know exactly. If this went through an oscillatory process, an underdamped process, or an overdamped process. Let's continue. So what approximate, I forgot to read that. The operator notes in the logbook that there's no change after 3:34 a.m. So at 3:34, it's not that he came after a long time. He realized that at 3:34 there's no change. Okay, so if I want to mention that my 3:34, okay, so at 3:34 there's no change. So I'm talking about 3:34 minus 309, where it first appeared to have a change, is equal to 25 minutes. So if I consider that it takes about 5 tau to reach its new steady state, here I can calculate tau to be 25 over 5, which is equal to 5 minutes. It looks like I found everything. Okay, it looks like I found everything. And by that, actually, I think it's asking about the transfer function. So what approximate transfer function to relate temperature to the flow rate in the absence of the more accurate information. We already have it, which is T prime of S over Q prime of S, which is equal to K. I did not find K. There's something I did not find. So K is equal to change of output over change of input, and the change of output was 4.7, which is 124.7 minus 120, and the change of input was changing the QI. The QI changed it of 40, so that is over 40, and then you're going to find that K is 0.188, and by that I have my K over tau S plus 1 e to the power theta S. Very easy, straightforward, and I have my system here. So that is the first part. It's asking me, of course, what do you need to do to get a better estimate? Of course, we need more data, okay, to get more estimate and a more accurate estimate. Okay, great. So now we'll go to 7.2. And 7.2 says that we have a single tank that has been operating for a long time with an inlet flow rate Qi equal to 30.4 feet cube per minute. After the operator increases the flow rate suddenly by 10%, so it increases by 10%, okay. It increased by 10%, that means it increased it from 30.4. If you add the 10%, which is 3.04, it will be 30.44. Okay, so if I look at 7.2, Qi was changed from 30.4 plus 10%, which will be 33.44. Let me make sure 3.04. Right, that's correct. So if this was that, so delta Qi or Qi prime that we already know is equal to 33.44 multiply minus 30.4. This will be equal to 3.04. And if I'm going to talk about Qi in this domain, that will be 3.04 over S. I don't know what's the question yet. I'm still in the process of finding the answer. So here we have this table is given to us in 7.2. And from this table, like, there are many ideas just coming to my head how we can solve this problem. But let us see what is requested, right? And let us see what is requested from this problem. Assuming the process dynamics can be described by a first order model. So we want to fit a first order model. Calculate the steady state gain and the time constant using 4 methods. Ooh, beautiful. That is really beautiful. So looking at the first part, from the time required for the output to reach 63.2% of the total change. So if I'm going to look at the 63.2% of the total change, let's go to my data. So my data is here. So what is 63.2% of the total change? As we said that we are going to take if you remember, it is equal to, so I'm going to take the data here, 6.52 minus 5.5, and then you're going to multiply it by 63.2 plus the initial value, which is 5.5. So doing this, I'm going to go to my board. Okay, so what I have here is just identifying the 63.2% value. So what is the H 63.2% value? It is 6.52 minus 5.5, and then I'm multiplying by 0.632 plus 5.5, and the answer here is 6.145 feet. And by knowing this value, 6.145 is something between these two. So you're like interpolating between 0.6 and 0.8. Okay, you're interpolating between 6.07 and 6.18. And by interpolating, it's going to be something like 0.74. Okay, so the T or the tau, in this case, instead of saying T, I'm going to say tau is equal to 0.74 minutes. So that was our first method. Okay, that was our first method using the 63.2%. What about the second method? The second method says that from the initial slope. Okay, initial slope, that means we need to select the first two values. And the first two values in this case is they are 5.75 minus 5.5 divided by 0.2 minus 0. So I'm going to select my first two values. Okay, so that is the second method. So I'm going to select at time is equal to 0 my first two values, which is h at 0.2 minus h at 0 divided by 0.2 minus 0, and this is equal to 5.75 minus 5.5 divided by 2, and this is equal to 1.25. And if you can recall that my tau my tau is equal to Km divided by dH by dt at t is equal to 0, and this is equal to 0.347 into the m, which is the step input, which is 3.04. And hold on, do you know how you got k? K is the change of the output over the change of the input. maybe I forgot to do this, but like it is just straightforward. So just to show it here at the beginning, we forgot to do this. So K is the change of the output over the change of the input, and the change of output over the change of the input is equal to 6.52 minus 5.5, which is the change of the output, over the change of the input, which is 33.3.44 minus 30.4, and the answer is going to be 0.336. Okay, 0.336. And going to my problem here, so in this case that I have here, this is not 0.347, it's 0.336. Okay, so it's like Km divided by dH by dt, which is 1.25 that I identified. And the answer is going to be, if you hold a moment, so the answer is about 0.817 here, so about 0.82. So that is how to calculate tau. And now if we look at the third method, which is C, another method, let us see what is that method. It wants us to find out through the slope of the fraction incomplete response curve. I think so that we have not taken the fraction of incomplete response curve, so I'm going to keep that out. As I told you, there are many different methods, and then it wants us to compare them. So I can just compare the 0.817 with the 0.74, and you can see there is a little difference between these two. So that was for 7.2. We had solved up to 7.2. Okay, great. So what about if I want to solve now 7.3? Let us have a look. Okay, 7.3 says that a process consists of two stirred tanks with input Q and output T1, and another tank 2 where T2 is affected by T1. To test the hypothesis that the dynamics in each tank are basically first order. So it's first order T1 to Q and then T2 to T1. A step change in Q is made from 82 to 85 with output responses given in E7.3. So where are my responses? Okay, here are my responses. And looking at that, actually if I want to see how T2 is changing, maybe it will be a second order, but maybe I also can approximate that to a first order process. So that is the whole idea. So find the transfer function of Ti with Q and T2 with T1. Assume that they are of the form of K over tau plus 1, the standard form of the first order. Then calculate the mode responses to the same step change in Q and plot the experimental data. Of course, we don't have experimental data, as it's not easy to plot now because we need MATLAB to do that. But we can find our transfer functions because we have our data here. And we can see here that we can use different methods as we said to find tau. So we can use the initial response or the 63.2%, whatever we see is suitable. But just to find K1 and K2, right? We want to find K1 and K2. So for K1, it is the change of the output. So what's the output? It changed from T1 changed from 10 to 18, and the input was changed from what was that value? It was changing from 82 to 85. Okay. So the change of the input is 3. Okay, the change of the input is 3. So back to our problem here, I'm going to write now 7.3. So the change of output is for T1. So I'm going to write delta T1 in this case. Let me write K1 and K2 directly. So K1 is equal to, for T1 is going to be T1 at 50 minus T1 at 0. Divided by, we already know that delta Q is 85 minus 82. So this is like 18 minus 10 over 85 minus 82, which is 3. The answer is 2.667. And to find K2 is equal to T2 50 minus T2 at 0. Again, by delta Q, this is 26 minus 20 divided by 18 minus 10, that is 0.75. So this is K1 and K2. Now for tau 1 and tau 2, as we said that we may use the 63.2%, or you want to use the initial 63.2% is good. Okay, so for the 63.2%, what should we do? 50 minus 10. Okay, I'll just show that to you. So I want to find that as 63.2%. So what I need to find, I need to find t at 63.2%, which means I need to find t1 at 63.2%, which is equal to 50 minus 10 into 0.632 plus 10, the initial, and that is going to be equal to 35.28. And as we find 35.28, we just go back here and says, where's 35.28? Okay, there's no 35.28. Come on. I used 50, it is 18. Oh my god, that T1 was 18. That's what I was wondering. So that is not 50, that is 18. So 18 minus 10 multiplied by 0.632 plus 10, so that is 15. That's about 15,056. So that is 15,056. So now we go back. Where's 15,056? It is like 15,06. So we can say that t is equal to 3. Tau is equal to 3. So here tau 1, we identified it as 3 seconds. Great. What about the second one? The second part, at about 63.2%, we are going to look at T2 at 63.2%, and that is equal to 26 minus 20. Okay, so 26 minus 20 into 0.632 plus 20, and the answer will be equal to 13, the answer will be equal to 23.792. 23.792. So that is equal to 23.792. So I would say that is about 23.8. So looking at 23.8, 23.8. Okay, now this needs an interpolation. And the answer is like between 4 and 5, right? It needs an interpolation, and the answer is between 4 and 5. So we will consider that tau 2, it's not easy to say that, but tau 2 is going to be like, let me see that, 22.8, it's closer to that one. So I would say that like 4.1, 4.1, okay? So tau 2 is about 4.1 seconds, just to make it easier and simpler and faster. So by that, I already have my response. So T1 prime of S over Q prime of S is equal to 2.667 over 3S plus 1. And for the second part, it was 2 prime of S over Q prime of S. Okay, over Q prime of S is equal to 0.75 divided by 4.1 S plus 1. 4.1 S plus 1. But hold on. Okay, so let's check. Was this K that we had obtained was for T2 with Q or T2 with T1? Okay, so I need to check up and check that again. No, that was T2 with Q. Okay, oh no, that was not T2 with Q. That actually was T2 with the T1, and here it was not delta T1. Oh my god. And because of that, now things are going to be a little different here, but I need to fix my K. I need to fix my K2, and fixing my K2, that means I need to divide that 85 minus 82, okay, 85 minus 82, so 26 minus 20 divided by 3, that will be 2. Okay, so the answer here is 2. So going up again, this will be 2 over 4.1 s plus 1. Of course, this k will be different. If you're talking about t2 over t1, it will be the 0.75 term that we had just mentioned. And actually what it will be if you want to calculate t2 over t1, which is like an intermediate between these two, now we will have the answer here 0.75. However, the answer here will be like 1.1, the difference between this and that, okay, s plus 1. So it will be something like that. So that is the solution. That is the solution of 7.3. So now we're going to continue with 7.4. So 7.4 talks about for a multi-stage bioseparation. So for multi-stage bioseparation, described, okay, what's going on with the with the reddish color here and there. Okay, so for multi-stage bioseparation, described by the transfer function, and we have the transfer function here. Calculate the response to step input change. Okay, calculate the response to step input change for 1.5. Obtain and approximate first order plus time delay using the fraction incomplete response method. Okay, we didn't take the fraction incomplete response method, but we have the other methods. So we are going to fit with other methods to this multi-stage bioseparation process transfer function. So what do we have in 7.4? We have g of s is equal to 2 over 5s plus 1 into 3s plus 1 into s plus 1. Okay, so fitting to a first order plus dead time, and well, it's not a fitting, we are approximating, all right? Okay, we are approximating. So we are approximating to a first order plus time delay, and that will be as simple as doing this. So that will be g of s is equal to, we keep the largest down there, and we can take the two other parts as e to the power minus 3s and e to the power minus s, and this will be 2 e to the power minus 4s or 5s plus 1. So that is using the Taylor series method, right? And actually, if I want to use the Skogestad method, well, the Skogestad method, if I want to hit the first order, I just want to make sure that I will get a good accurate approximation or not. So using Skogestad method, we just want to make sure that tau 2 over tau 1, which is 5 over 3, is greater than 1.5. 5 over 3 definitely is greater than 1.5. So we will have a good approximation, okay? A good approximation is expected. And by that, it means that now I can do my job of approximation. If we just can recall our g of s. So if our g of s is equal to 2 over 5s plus 1 into 3s plus 1 into s plus 1. So my case cog, okay, well, if you can recall, yes, that's fine. My case cog is equal to 2. My tau's cog is equal to a largest plus half of next largest, which is 1.5 plus 5, 6.5, and my theta's cog, which is half of next largest plus the remaining, and remaining is only 1 here. So I'm going to have 1.5 plus 1, 2.5. So my g of s, or my g's cog here, the approximated one is 2 over 6.5 s plus 1 e to the power minus 2.5 s. Okay, so that is how to approximate to first order. We already did something with second order, so we are just looking for different and more examples. So going to 7.5, okay, so here I'm going to solve 7.5. Fit an integrator plus time delay. we can fit an integrator plus time delay, by the way, but I would prefer to do something else actually, because we want something that is more accurate. To the unit step response in figure E 7.5 that I have in front of my eyes here, the step response have been normalized by the steady state gain. Compare the experimental with the response obtained here. So this is what I have here. Like if you have MATLAB, you can run our expected response with this data here. I don't know how we're going to enter this data. At the end of the day, we also need some kind of human error that we have to approximate that data. Okay, so what do we have here? We have several things that come into our mind. So the first thing that I'm going to use the slope intercept method. So I'm going to use the slope intercept method, and using the slope intercept method, I'm just trying to make a straight line here. Let me say that is about 0.9. Is this a good thing that I did here, or it looks bad? Okay, so let's do our best again. So it's something like that. Okay, it went little up and little down there. So let's say that's about 0.9. Okay, so what I'm saying here is that this goes from 0 to 0.9 at a steady state. What else do I have? What I want here is to look at the inflection points. It's not easy to get the inflection point, but the line I would expect that goes through the inflection point is here. So this is theta for me, and in that case it looks like 1, 2, 3, 4, 5. So it's 1.5 maybe. Okay, so it's like 1.5. Okay, actually it's more towards 1.7 maybe. It's 1.72. Okay, I'm just kidding. I mean, it's not that accurate with my eyes, so I would just say 1.7. And then we take the second part here where it says 15. So 15 minus 1.7 is tau, right? So from here till here, from this point till this point is tau. So that is 15 minus 1.7, which is 13.3. So I found tau and I found theta. Now I just need to find k. K is the change of the output over the change of the input. And the change of the output is 0.9 minus 0. What about the change of the input? I don't know what's the change of the input. Fit an integrator for a unit step. Okay, it said a unit step. That means the change of the input was 1. So k is 0.9, and I have my model here. So my model is going to be k over tau s plus 1. So it's going to be 0.9 over 13.3 s plus 1 e to the power minus 1.7 s. Okay, so that was 7.5. That was 7.5. And I think so that was a good example that we had taken. Okay, so going to the next problem, 7.6. Estimate the following models using the graphical model. Let me see if I'm going to solve this. Well, this needs a linear regression, and we did not take linear regression, so I'm going to skip up this part. And let me see, 7.7. 7.7 is good. I like this. Okay, so 7.7. So here I already solved 7.5, by the way. So 7.7. A heat exchanger used to heat a glycol solution with a hot oil, known to exhibit first order plus time delay. G1 is equal to T prime of Q. So T increases as heat is increasing, or heat. The heat that is used to heat up the system, that's why the temperature increases. T primes the output temperature deviation, and Q primes the hot oil flow rate deviation. A thermocouple is placed 3 meters downstream. Okay, when it says thermocouple is placed 3 meters downstream, that means there was a delay for this thermocouple to detect that the temperature had changed. So it's 3 meters down. And what did it say? It said the average velocity of the glycol in the output pipe is 0.5. So I can guess here directly that theta is equal to 3 over 0.5 is equal to 6. Okay, 3 over 0.5 is equal to 6. So I got theta here. And actually, this is just saying that there's a delay here. The thermocouple is also known to exhibit a first order behavior. However, its time constant is expected to be considerably smaller than the heat exchanger time. So what I'm saying, the thermocouple is exhibiting a first order. The thermocouple, because it's a thermocouple, yeah, it has this k over tau s plus 1, and usually for a thermocouple, okay, so I'm going to write this here. So first I obtain theta, which is equal to 3 divided by 0.5, so that was 3 meters over 3.5 meters per second is equal to 6 seconds. And why is that? It's because that I had a thermocouple a bit within a distance, okay? It's measuring within a distance. So if the thermocouple is measuring within a distance, so this distance is like the temperature is changing here because of the coil, but I measure the temperature after some distance, which means there's a time delay in which the temperature had changed and the time that I'm really attempting to achieve this value here. Okay, so that is the idea. So if you change Q, T is changing. So there's a relationship between T and Q. Okay, so there's a relationship between T and Q. And we also have another relationship between T and Tm and T. So when T changes, Tm changes, but however it takes some time. Now for Tm over T, it is equal to k over tau s plus 1. And since both of them, this is like a sensor to the temperature, so the change in the output is like the change in the input, because sensor will tell you exactly what is happening. So that will be 1. So that will be like that will be 1 definitely, to the e to the power minus 6s, which is the time delay, over tau s plus 1. Now the tau for the thermocouple is really quick, really fast, and just we will assume, like for example, it finds that for example in a millisecond, okay, like 0.01 second plus 1. So it's like very instant, very good thermocouple. And this is like, for example, so I assumed here, based on my knowledge of knowing what is a thermocouple, I assumed a value for a thermocouple that it has a very fast response. So I assumed a fast response for a thermocouple. And we are going to see what will happen because of this assumption. That's a good assumption, by the way. And that will help me a lot. Okay, let's continue. So data from a unit steps test in Q prime on the complete are shown in figure 7.7. Using a method of your choice, calculate the time constant of this process. Okay, and then we don't want to do the empirical model. We just want to work on this. The chapter 7 has more than one part. We explained what you need for which is required in this subject. The other parts that I'm skipping is not required. Okay, so this is what I have here, and it's very obvious that I have a time delay here. There's a time delay here. So it told me to select something of my own selection. So I can use the 63.2%. I can use the slope intercept method. I can also use the, for example, I can also use what they call, sorry for that, I can use a Smith method as well. Okay, I'm just having this in my mind. Smith method, where I can find the T20 and then I find the T60. Okay, all right. So all of these are just going through my mind. So the first thing that I could say that there's a time delay here. There's a time delay for Tm, how it reacts with time. And actually the time delay I found was 6. I don't know why it says 4 here. Why does it say 4 here? It's 3 meters and 0.5 meters per second. So it looks like if that was 2 meters, that makes sense. So I don't know why it said that. Okay, whatever. Okay, so this is how Tm reacts as changing with time. But I already have the system here. Okay, so consider where the T is the output temperature. Actually, this is not TM. Let me make sure. I don't think so that is TM. I think it makes more sense if it is T, the temperature. And this is how it gets affected by what's getting in the system. So let me see. We have T over QS, where T is the output temperature. And what do we have here? The data from a unit test in Q prime on the complete system, figure E 7.7, using a method of your choice, calculate the time constant. So I will consider this as T. I think so. This goes as T. It doesn't make sense for me to be TM. And here I have like a time delay here, and now I'm going to draw my system. So what I'm going to do, I'm drawing my system here as a slope intercept. Let's do it with more than one method and see what goes on. Okay, so this is like here. Okay, something like that. And this is like more than 9 in my eyes. It's like 9.2, for example. So 9.2 minus 0, so delta y over delta tu, which is k, is equal to 9.2. And what did it say? It said that it was a unit step. I think so. A unit step, right? So it's 1. The delta u was 1, so it's 9.2. So here I'm going to say that my k, my t, okay, my t with the q is equal to, the k here was equal to, what was that? What was 9.2? What about tau? Okay, what about tau? So tau here is, if I take as this example here, okay, I'm trying to fit a first order plus time delay here. So here I have 11 and here I have 4. So my tau is equal to 11 minus 4, which is equal to 7, and my theta is 4, so theta is equal to 4. What else do I have? Okay, I found all my parameters, so that will be 7s plus 1 e to the power minus 4s. So what do I have here? I have t of s over q, tm of s over q of s is going to be something like that. Is a multiplication of two systems in series, like two transfer functions in series. So I'm multiplying these two transfer functions plus 1 e to the power minus 6s. And what do I realize here? Actually, what I can realize here, is that this is very far away from the imaginary axis if I compare it to this one. So this one, it looks like it is negligible. It is negligible if I compare it to the original, to the 7s plus 1. And this is why this part, which is referred usually to as GM, and you're going to take that in control, and this is like GP. Okay, usually GM is approximated always as 1, and the reason that it is approximated as 1, because the K is always 1 for a sensor, and the denominator is cancelled out in comparison to the other dominant poles. So this is why it goes back to like 1. So we are just left with the delay only, and left with the delay we are going to have something like 9.2 over 7s plus 1 into e to the power minus 10s. There's only one thing that I need to fix up here, is that here instead of saying e to the power minus 6x, actually this was in minutes, and everything was in minutes except that the 6x was in seconds. So what I'm trying to do here, I'm going to remove the 6 and say that's the 6 seconds, okay, 6 seconds over 60 seconds into 1 minute, it is equal to 2.1 minutes. Okay, now it makes sense for me. I was just wondering why this number is really big. Okay, so the delay is 0.1 second. Now it makes sense for me. And talking about 0.1, this will be like e to the power 4.1 second, and that is much better if you look at it. So great. So this is what we had obtained. from our problem here. And actually we also can use the using the Smith method. I don't know if you would like to use the Smith method. Why not? Why not? Sometimes it's good to solve problems with the different ways. So using the Smith method, where we want to fit a second order plus time delay. Okay, I don't know if you want to fit a first order or a second order plus time delay in this sense. But as you remember, Smith method, we are trying to fit to find k, tau, theta, and psi. And since it's psi, so that is definitely fitting what? Fitting a second order plus time delay. And in that sense, I'm going to start doing my process here. Well, the thing that you need to consider when you do the T20 and T60 to find out the values of T20 and T60, don't be confused of the time delay that is available, because the time delay could be very tricky in this regard. So the theta here, which is time delay, is 4 minutes, right? So if I just remove things out here to just work on my Smith method, so everything, please go away. Yes, please. I'm going to start. So I have theta is equal to 4 minutes. So if I take T20, okay, T20 between 9.2, okay, 9.2 minus 0, and you multiply that by 20%, so it's about 1.8, right? So taking 1.8 here, this is T20. Okay, so T20 is something like, if I would say 5.6, for example, so I would have T20 is equal to 5.6. Okay, here's the problem. This is not correct. That is not correct. Why? Because actually your T20 was not 5.6. Your T20 plus theta was 5.6. And your T20 was actually only 1.6. It was 1.6. Your T20 was that small amount here only. Okay, was just that small amount only. It should not consider that time delay. So please don't confuse that. And similarly, if you want to calculate T60 into 9.2, so that will be something like T60 will be like 5.1. And if you go to T60 to 5.1, and you're going to find this is like 9 point something. So if I say that T60 plus theta is equal to 9.1, so T60 is equal to 9.1 minus 4 is equal to 5.1. So you can see that I already have found T20 and T60. So here I will say that my T20 over T60 is equal to 1.6 divided by 5.1 is equal to 0.314. So now I have the value of 0.314. So if you just recall of what we had taken before, so this is my figure here, and what do I have? I have 0.314, and looking at this 0.314, okay, T20, see T20 of T60, 0.314, I can find the value of T60 over tau. And where's my T60 over tau? It is here. So the value is about, I would say T60 over tau here. It is something like 3.1. Let me say 3.1, okay? And if I would go really higher also, okay, just to find the value of xi, okay? So I'm going to find that the value of xi here is about, it's about something like 1.9. That is a bit high, right? That is really a bit high. And actually the only thing that you need to consider here, this is like 1.7 or something, right? Something like that, if my figure is correct. So my 0.31 actually should be more to the right, okay, more to the right. So I will consider this because like 1.63. So what do I have here? What I'm trying to say here, definitely this is going to be greater than 1, and it should be an overdamped process. Why? Because my figure was what? If you go back to my figure, So the figure that I have, it looks like an overdamped process. It's not oscillatory. So if I'm going to fit a second order plus time delay to this figure, definitely my xi is going to be greater than 1 to show that is an overdamped process. So in this case, what do I have? I have my value of xi, which was 1.63, and I had T60 over tau, which was equal to 3.1, where I can identify the tau to be 1.645. And in this case, having the value of tau, what else do I have to find? I just need to substitute, and substituting, I'm going to have k, I already have the value of k over tau square s square plus 2 xi tau s, and we already have the value of xi and tau plus 1. Okay, so all what you need now to do is substitute, and in substituting you're going to get the answer, right? And so I'm not going to do the step here, you just need to substitute. So please substitute. Okay, just substitute what? K, tau, theta, of course, and xi. So I don't want to forget theta because we already know that this is e to the power minus 4s. Okay, beautiful. So that was the answer that we have found through more than one methodology here. It was beautiful to find out how to solve 7.7. Okay, I think so we had taken good number of examples, and actually from all what I see in front of my eyes is just my eyes is playing around. My God, I like to solve all this. I love to solve all these. Okay, so if you look at 7.10 is very interesting. I like this. Okay, so I'm just going to use the idea of 7.10 so that we can solve using one of the methods. Okay, so it's not more than I'm trying to solve here what is requested by the problem. It's more like what I'm trying to use here as an information. And actually I did not read the problem. Maybe it wants the same thing. What transfer function can you get? Yes, that's what I want exactly. And then if there is a ramp input, what you're going to do. I'm not worried about the second part. So what transfer function approximately describes the operation of the process 7.10? Provide units for all parameters. So what do I have here? It's a second order shape. It's an underdamped process. And since it's underdamped, which means I mean underdamped, it's oscillatory, it has complex roots in its denominator. What's most important is xi is less than 1. Okay, so I can use the damping method or I can use the Smith method. Okay, the damping or Smith method. Let's use that. I always advise to use the damping method if you have some kind of oscillatory system like that. So this new steady state value that I have, and which is not easy to obtain, it looks like here it looks like 156, for example, I would say. So that is like 156. Okay, 156. So that is my new steady state, and it starts at 140. Okay, so delta y is 1 minus 156 minus 140. And what was the delta u? Let me go back. It said here what transfer function describes the operation of the process. So it did not mention exactly, but I would consider that delta u is 1 here, for example, because it did not say actually. It did not say. I cannot say anything. So if we say delta u is equal to 1, then we can find out the value of k. So I'm just going to assume that delta u is equal to 1. So 156 minus 140 divided by 1 is equal to 16. Okay, so this was k is equal to delta u over delta y over delta u, change of output or change of input is equal to 16. So I got k. Okay, now I find the value of k. So let me go here and write 7.10. Okay, so 7.10, I found the value of k to be 16. What about tau? Okay, now before going to tau, I always advise that I should find xi before tau. So here I have the overshoot. The overshoot is a divided by b. And how beautiful. I have a and I have b. So just going, I need to say that my overshoot which is equal to A divided by B, which is equal to 161.5 minus 156 over 156 minus 140, and you're going to find that this is equal to 0.344, and we already have an equation for the overshoot. And the overshoot equation was, if I can remember, it was exponential minus pi xi over square root of 1 minus xi square. I think so, it was like that. And based off what I have written there, you're going to have your answer. Actually, I'm not sure of this equation here, but please check that equation. But when you do your substitution, you're going to find that xi, because it is oscillatory, definitely is going to be less than 1, and we found out that it is less than 1, and it was found out to be 0.322. Great. Now the question is how to find tau. So we need information, okay? So to find tau, we need information about something that has the time information, which means I may need TP or TR or settling time or time period. Let me see what do I have. What I can see is very difficult to identify that the period here, because the second oscillation is not that clear. It's very flat. But actually the TP is something that I can identify here. And if you look at that, that TP is about equal to 33 minutes, and through my TP I can find through the equation, and through the equation of TP that will be given to you, I can find the value of tau. And the value of tau, if you calculate it, you're going to find out that it is equal to about 9.5 minutes. 9.5 mints. Okay. So this is the idea of the whole thing here. I think so. I found out all the terms. I found tau, theta, xi. Do I have a time delay that I should subtract? I had no time delay. That's why my TP was also not subtracted from anything else. Okay. So all what I need to do is to substitute. So I have all my parameters here, and I just need to substitute. Okay. And if you use Smith method here, sometimes it is confusing, to be honest. Why? Because you have it very oscillatory, and your T20 is going to be somewhere here, and your T60 is going to be somewhere here, and then you're going to find the value of xi and so on. And let us see, are we able to find out that using the T20 and T60 of the Smith method? Well, I did not check that, by the way, but why not? Why not? I think it's my last problem for today. So let me see the Smith method. And looking at the Smith method, the T20 is like between 140 and 161.5. And if you calculate this, the answer will be, so if you continue and see that my T20%, so what I'm trying to do to find out here is I have the numbers is 161.5 minus 140, so I need to find the T60 T of 20%. So that T20% at the temperature of 20%, which is 161.5. Hold on. So I need to go to the steady state value, not the maximum value. So my steady state value is 156. So here it's 156, okay, 156 minus the first initial and the final steady state value into 0.2 plus 140. And by that I can calculate this, I think. So this is like 16 into 0.2, which is 3.2, so that is 143.2. And 143.2 degrees centigrade, if you go here, it's something like 143.2, okay? So it's going to be something like, say 8, no, that's 8 for example. So T20% here, I'm going to consider it as 8 minutes. I think we are dealing with minutes here, right? And if you go to T60, so T60%, So if I want to find T60%, which is at T60%, okay, sorry, it just told me that my battery is low, okay, and T60% is equal to 156 minus 140 into 0.6 plus 140, and 16 into 0.6 is not that straightforward, it's 9.6, so it's 149.6 degrees centigrade. If you go back and see where's 149.6, which is about 150, so this is something like 20 what? This is like 10, it's not 15, 15 is here, so I'll say 14 for example. So let's say 14, okay? So T60% is equal to 14 minutes, okay? So what is T20 over T60? T20 over T60 is 8 divided by 14. And 8 divided by 14 is equal to 0.57, okay, something like that. And looking at 0.57, if you go to your figure here, and it's very critical, okay, so somewhere here. And if you look at the T60 over tau is about 1.2, for example. So T60 over tau is about 1.2, and my value of xi is not easy to find out this, by the way. And but I will have an idea. What did I get the value of xi for the first one there? It's 0.322. So it could be my approximations here are not that accurate, and actually this is not 8 divided by 14. I would say like this is 8 divided by 13. Oh, sorry, 8 divided by a bigger number. Okay, so 8 divided by, I'll say like 14.5 or 14 point something. So it's like more like a 0.55 thing. Okay, but if you're more accurate, you can get things really neater, right? So if I say that is 0.55, just to get closer to something that's making sense here. So this is like 0.55, and now this is like 1.4. It's about 1.35, let me say, and my value here, which is not easy to identify here, because it will be somewhere here like 0.3 something, right? 0.3 something. So we'll say that is about 0.32. Very, very tricky and lazy. I don't know what to say about that. So my T60 over tau, is 1.35, and my xi was equal to 0.32. So what is tau then, right? Tau is equal to T60 divided by 1.35, and what was my T60? My T60 was 14.5 divided by 1.35, and that is equal to 10.74. 10.74. So I found out the values here, right? I found out the values. What was the value before? It was found by 9.5, right? So here it was about 9.5. I found that using the Smith method to be about 10.74. So I'm just telling you that you can find out using the damping method or the Smith method, and all of them will just track you or pull you to the same, something very similar to as an answer, and you will have a figure that is looking really great. Okay, so that was for 7.10. That was 7.10. You can solve more problems, but this is the end of it, because from 7.11 it starts with something called discretization, and using the difference method, you see the finite difference approximation, exact discretization. Here's the end of our problems. It's at 7.10. I hope that we had done a very good job today, and I'm going to put some kind of colorful hair here. Oh my god, this is the dark hair, okay? So all the best. We had done a very good job today, and please enjoy your time, and good luck. Ma'a salama, and all the best.